I actually found mine.
I have a question.
Yes.
For the PA5, should we do presentation?
Should you what?
Should we do presentation for the class?
No.
Oh, just.
It's a group project, but you don't present.
Okay.
So we presented the travel reservation system because I gave you a lot of leeway in how you were going to design it and such. So I wanted you to be able to demonstrate that. But PA5, I'll just grade myself.
I actually have a question as well.
Mm-hmm.
Is there a specific way you want to do error checking? If this error occurs, you want to do it only this way? Or is there a way we can do it?
You mean, do I care how you detect the error or how you respond to the error?
How you respond to it?
If there's a problem in the knapsack file, if there's a negative weight or a negative capacity or zero capacity, if there's no argument given, if it's not a valid argument, if the contents of the file are corrupted or if the file's missing, those are all conditions under which you're allowed to tell the user there's a problem and then just exit. Okay, so if you give them a lot of information or a little, I don't care if you do something different, that's fine. But don't segfault and don't just run with random information. Okay, those are the main things. Do something controlled and deliberate. So my suggestion would be just print a message, you know, the knapsack data file is missing, or, you know, record 3 is corrupt, or you can't have a negative capacity or whatever, and then just do an exit or a return. I'm not going to heavily stress test it, but I will try a data file that has garbage inside. So you definitely want to check for that. So what?
So we're trying to make a compiler
For the data file? Yeah, basically. Definitely doing some parsing and syntactic analysis. But you don't need to write a BNF for it and so on. I said BNSF. All right, I brought my playing cards today. So let's do hearts. So we did bubble sort the other day, right? We kind of broke into that, and we saw the order complexity was what? N squared. And there's variations possible, but it still rounds out to n squared. So let's look at two other kinds of sorts that are also n squared. So I'm going to use a full deck of cards here, including these, just because I like the artwork. So the ordering we're going to use, remember we always need an ordering. In case you don't play blackjack. Ace is a 1, Jack, Queen, King are 11, 12, and 13. So here's a set of cards, kind of randomly ordered. So let's look at a selection sort. So here's the basic pass that we do in a selection sort. Pick smallest number, add to the output, and repeat n times. So how does this work with a stack of cards? The cards are our input, the output's going to be this column over here. So we're going to go through, we're going to pick the smallest number. How do we do that? Well, our first number is 8. That's the smallest number we've seen. That's bigger. That's bigger. 7 is smaller. So that's our smallest. 10 is bigger. Ace is smaller. That's a 1. That's our smallest. 3 is bigger. 2 is bigger. King, 9, 4, 6, 5. Those are all bigger. So ace is the smallest number in our cards. So we're going to take that and we're going to put it in our output pile. All right, and then we're just going to do this again. We're going to start at the top of our input. We're going to find the smallest number. Well, that's an 8, and 7, and 3, and 2. And 2 is going to be the smallest, so we'll take that. and we'll add that to our output. Pretty straightforward, right? Each pass we go through and we record the smallest number that we found. And when we get to the end of our input, whatever that smallest number was, we add that to our output. Now the process of finding the smallest takes roughly n operations, right? And that n goes down. Initially it was 13, the second time it was only 12, and so on. But just like bubble sort, it's basically n operations per pass, and each pass puts one card into the output. So if we have n cards to sort, it's going to take n passes. So this is still going to be an order n squared. Each pass is n, and there's a total of n passes. Sorry, say again?
Yeah, you took one out. Doesn't go down by 1. And so you do n.
Well, so it's technically n plus n minus 1 plus n minus 2.
Oh, I see.
Right, so we're back to this.
That's the n times 2.
That's the n times n plus 1 over 2. But that's still order n squared. That's okay. So selection sort, right? We're doing the work in choosing which card comes out of our input. Okay, so what does this look like with code? So for pass equals 1 to n, so this is selection sort on n things. So we do n passes, and at each pass, I'm going index origin 1 here just to mess you up. So set the minimum equal to the first data value, and then for I equals 2 to n, if data I is less than min, set your min equal to data I. And when you come out of this, min will be the smallest element, so add min to the output. And then somehow, with the cards, we removed it from the input. And we repeat that. But there's some details here, right? So how do we add it to the output? Well, we have an output array. We know how many things are in it. So output array bracket number of things equals min, and then increment the number of things by 1. That part's easy. How do we remove it from the input, though?
Could have an if statement when you're going through it, and you could set a value, some sort of value that would signal flag.
So we could mark a flag. So when we come through here, we're finding the smallest value. It turns out to be an ace. Okay, so we copy that to the output, and we're going to flip it upside down. Okay, so we have a flag associated with each number, and that flag says whether or not this number's already been sorted out. And now when we look for our smallest number, it'll be a 4, and then a 3, and then a 2. So 2 is the smallest. So we'll add 2 to the output and flip that over.
But if we're using integers, then like if we were to do this with integers, then if someone were to input integer, that would map to the flag.
So you need like integers flag, right? So make a structure or something. Yeah. So that's just the number of passes we're going to make. We don't use it. It's just counting how many times we want to do this. Because each time we do all of this, it takes one number, the smallest number we haven't sorted out yet, and adds it to the output. It's just counting. So we've done this 2 times, and we've got 2 things on our output. Let's do this again. 4 is the smallest. 3 is smaller than 4. Okay, 3 is our smallest. Let's add that to the output, and we'll clear the flag on that. Okay, we've done 3 iterations of this, and we've got 3 numbers on our output. Well, how many iterations should we do? If we have n cards in our deck, we need to do this n times so that we get n things in our output. So this is just saying let's do this inner part n times. Okay, it's like the pass we do on the outside of the bubble sort. Each time we go through that inner code in the bubble sort, the largest number remaining falls down to the bottom. So we have to do that a total of n times. So this is just doing this inner loop n times. Another option, instead of removing the minimum from the input, would be to set it equal to infinity. And if your system has a notion of infinity, that's pretty easy to do. And then it's never going to be the minimum, so it's basically going to ignore that number. And one way you might do that is go through and as you make your first pass, see what the largest number is in your array, and then just use that value plus 1 as your value of infinity, and it'll never be the minimum after you set it. Or you may not be using an array at all. You may be using a linked list to store your data, and we can do a selection sort on a linked list. Start at the beginning, march through, and find the smallest value. But remember where that smallest value is. In fact, remember the node right before it. And then after you add it to your output, just delete it from your linked list. And that's very efficient. The other option is to actually go through, and if you have a set of values and you want to delete this, you could copy everything up one spot and then just reduce the size of your input array by 1. That's not efficient, but it's still order n. Sorry, n squared. It's still order n for that one pass. Right? It's actually 2n, but that's still order n. So there's different ways that you can work this in code. But again, it's an n squared, so it's not a very commonly used sort, because bubble sort's a little easier to implement. Okay, that's a selection sort. And the way to remember that that's selection sort is that each pass, you're selecting the smallest number that you have. Okay, the sorting operation takes place in that selection, as opposed to an insertion sort. And here's how an insertion sort works. You don't worry about making any fancy selection. You just take the top number, the first number in your array, but you insert it into your output array so your output array is always sorted. So take the first card. There's nothing in the output array yet, so that's going to be our output. Take the second card. That's a 6. Should that come before or after the 9? It should come before. Take the next card, that's a 5. Should that come before or after the 6? It should come before. Take the next card, that's a king. It should come after the 5, after the 6, after the 9, so it goes right there. And so we're building our output pile by taking each card in order from top to bottom and inserting it into the output in the correct spot. So insertion sort, take top card from the input and insert into the output in sorted order. All right, so selection sort we take from the input pile in sorted order. Insertion sort we insert into the output pile in sorted order. All right, that's the distinction between them. Are you sorting when you take the cards from the input or when you place them in the output? So how do we do this? Well, we're still going to need n passes because each time that we take a card, it's going to leave the input, it's going to go into our output, and it's going to take a total of n passes to sort the entire array. So insert insert first number into the output array. Well, it's a little easier if we actually start with the end of the array, because we can remove things from the end of array by just decreasing the size of the array. Right? So let's actually insert the last number into the output array. And how do we insert into the proper spot in the output array? Just start marching through from the beginning of the output array to the end, and as soon as you find a number bigger than the one you're inserting, that's where it goes. This is how you insert it into a linked list. Right? As long as it's always sorted from smallest to largest, just start marching through. When you get to a spot where a number is bigger, you want to insert right before that. So for an array, you do have to do the work of moving everything down one spot. And that's what makes this pass and order n operation. For a linked list, you can just pop it right there, but it's still order n to get to that point where you're doing the insert. So this will, if you're doing an array, it will truly be an order n on the inner pass, but the length of that output array is growing, right? So it's really order 1 the first time, order 2, order 3. So it's still n times n plus 1 over 2, total of n passes. So this is still order n squared. Okay, so selection, you sort when you take from the input. Insertion, you sort when you put into the output. All right, well, let's do better than n squared. So let's look at a merge sort. And this is order n log n. I'm pretty sure. We'll find out. All right, I have 13 cards here to sort. Here's the idea of a merge sort. I'm going to take roughly half of those numbers, the first 6, and I'm going to say, can you sort these for me? And I'm going to take the other half and say, can you sort these for me? Okay, and I'll do your job for you. All right, so she comes back, and there's the sorted set of numbers from that first half. And this set of cards comes back, and that's been sorted. 1, 2, 4, 6, 8, 11, 13. All right. I'm not worried about sorting those two halves. I'm going to hand those off to other entities to sort. But once I get those back, here's what I'm going to do. I'm going to mingle them together. I'm going to interleave them. So how do I do that? Well, I take the smallest of the two entries that are on top. That's a 1. And I put that in my output. And now I take the smallest of the two entries, that's a 2, and I put that in my output. Take the smallest of these two, that's a 3. Take the smallest of these two, that's a 4. Smallest of these is a 5. 6 and 7 is a 6. 7 and 8 is a 7. 8 and 9 is an 8. 9 and jack is a 9. 10 and jack, 10 is smaller. 11 and 12, 11 is smaller. 12 and 13, 12 is smaller. And 13 and nothing, 13. And I've sorted my array. So a merge sort is really easy to do. Step 1, split input into 2 subsets, which we'll call left and right. Sort the left half, sort the right half, and then interleave those sorted pieces. All right, how do we do that interleaving? Well, you have two arrays. We start with the first entry in each array, so you need a pair of indices, right? Left index, right index. And if left index is smaller than right index, set your output equal to left index and increment left index. So we can do something like that. So if left index is less than right index, so left index and right index get initialized to 0. If left index is smaller than right index, then out bracket outsize equals left index plus plus, else outsize equals right index. And we loop through until we've used up both sets of inputs. And we have to be a little careful here, because it's possible that one of these arrays, left or right, will get used up before the other. And if we find that we've taken all the cards from the left pile and we still have cards left in the right pile, well, it's easy. We just take all the cards from the right pile and that goes into our output. We no longer have to interleave, right? But as long as we have cards in both the left and the right array, we have to find the smaller of the two, copy that to the output, and adjust the corresponding index. Yeah?
So you said this sorting way is easy. But
This?
only that one?
Yeah.
The algorithm. Because like for the step 2 and 3, it has result sort anyway.
So steps 2 and 3, we have to sort the left and right pieces. How do we do that? Merge. Just call merge sort. So merge sort will use itself to sort the two halves and then actually interleave them. We need some code for interleaving, which means we need a base case. So if n equals 1, then there's nothing to sort. And each time that we split into two subsets, the size of those arrays are going to get smaller and smaller. And so eventually we're going to get down to an array of length 1, and we don't have to do any work to sort it. We just copy it to the output, and we're done. So this is nicely recursive, right? We sort in two halves using merge sort, and then we put them together. And the only code we need to write is this stuff. But it's annoyingly tricky to write this, because particularly in C, arrays just aren't that nice to work with these kinds of operations. For example, when you want to split an array in two, I mean, we can grab the left half by just taking our original array and saying, okay, it's no longer 13 elements, it's only 6 elements. And we've got an array of 6 elements. But to take those remaining 7 elements and say this is an array, we've got to do something different, like pass the address of element 6, right, instead of just the array, and say that it's 7 elements long. And that starts getting a little annoying. And this business of one of the arrays hitting the end is some special cases you have to code up. So we don't want to compare to right index if right index is bigger than the size of the array. So we need a special case there. And then trying to return these arrays after you've done this interleaving takes some handling. So it's a little annoying to actually code this up, but algorithmically, it's pure simplicity, right? How do you sort an array, put it in two halves, sort each half, intermingle the two sorted pieces, and you're done. Yeah, so that's another annoying detail. If you have an odd number, you got to make a decision where you're putting that halfway point. And there's nothing magic about the halfway point, right? I could do this by just taking a few cards and another stack of cards, sorting each one, intermingling, right? But you'd like your stacks to be as small as possible. And the closest you're going to come to that is if you cut your original set roughly in half.
amount of, like the number of splits to do to sort the most efficiently.
Yeah, I don't know what you would get with that, because you can do this 3 ways, right? You can split it in thirds, and your if statement just becomes a little more complex. So if left is less than middle and left is less than right, then go ahead and put that in your output. And I don't know where the sweet spot is as far as total number of operations. It's a really interesting question.
Well, if you have an egg drop type of program to find that based on a certain number,
Mm-hmm.
and then you could just use that to, and then you could pass that number off to the program and it could respond.
Right,
With
right.
the optimized
Yeah,
sort.
that would be interesting. So I wonder how much work it takes to make that decision.
Because, I mean,
Yeah.
you're putting a lot of work into finding the best that it could be counterproductive.
Right.
Because I'm guessing that we're looking at n log n right now.
But there may be some way to characterize it first order, like split it into 2, 3, or 4 piles. And there may be some quick analysis you can do that gives you that answer. Hopefully people are writing these things down when they come up with these ideas and actually pursuing them, because I think these are all like interesting. And it's going to be a lot more fun than like write an ODP that takes 2 numbers, right? So.
Yeah, because I noticed that my voice does not get picked up by your microphone.
Oh, really?
It does not.
Okay.
So
So yeah, make notes. Cool. So when I grade large numbers of papers, this is actually what I do in combination with an insertion sort most of the time, right? Although names that start with like a W, X, Y, or Z, I always put in a separate pile because there's a few of those and they're easy to just sort of sort brute force. But then I kind of go through and I put them in order in a pile until the pile gets to be kind of big, or I get lots of things that are all close to each other, and then I start a second pile, and sometimes I do a third pile, and then I do a merge sort. I interleave those. But it's a fairly imprecise algorithm. It's never the same twice. And from class to class, there's always a letter which sort of dominates all the other names. There's some classes where I'll have like 30 people in class, and there'll be like 10 people whose last name starts with the letter E. And it's just like, why? I don't know. So these are practical. So order of complexity, right? N log n. Doing this interleaving is basically n operations, because you have n over 2 cards here, n over 2 cards here. You've got to go through all n of them and put the right one into the output. So it's order n to do this interleave. And when we split in half, right, we're working on a problem that's half as big. So if we start with 16 cards, well, we're going to sort an 8 and an 8, and we're going to interleave them. That's going to be 16 operations. When we try to sort the 8 using a merge sort, we're going to split it into a 4 and a 4. And then we'll have to interleave those. Well, that's going to take 8 operations. And over here, we'll split this 8 into 4 and 4. And when we interleave those, that'll take 8 operations. So at this level, we're going to have a total of 16 operations. And when we come down to 2 and 2, that's going to take 16 operations. And when we come down to 1 and 1, that's going to take 16 operations. But then we're done. We don't have to go any lower. So it's n operations for each level of our tree. And since the levels of our tree is roughly the log of n, right, this is a total of log n times that we have to do that n operations. So that gets you to n log n, rough approximation. So way better than a bubble or insertion or selection sort. More of a headache to set up, but once it's set up or someone set it up for you, then it's a joy to use. No. So there is no best, right? It really depends on the data. So we're going to talk about a Quicksort. And Quicksort works really well. It's n log n, unless your data is close to sorted to begin with, and then it's horrible. It goes down to n squared. So it varies, and it depends on the nature of the data.
So can you compare all the sorted and source way
So you can look at average case, you can look at best case, you can look at worst case. And there's no well-defined algorithm to say this is the best sort. Okay? It kind of depends on what you're doing. And remember, this might be n squared. This might be n log n, which sounds better, but there could be constants in there, right? This might be n log n, but up to 1 million pieces of data, your bubble sort might be quicker. But when you get above 1 million, your n log n might be more efficient.
Do we have any sorts that are better than n log n?
Yes, we do. So let's look at one. So let's look at a radix sort. And the tricky part with radix sort is getting the order correct in the algorithm. And there's about a 30% chance I'm going to get it wrong if I don't cheat, so I'm going to cheat. All right, so here's some numbers we want to sort. And there's n of these, it's some big number. Okay, here's how a radix sort works. We look at the least significant digit, and we sort just based on that. Okay, you can use whatever sort method you want. So just looking at this rightmost column, our smallest number is 5560, 5541, 6222, 3185, 4276, and 2147. So that's based on these. Now we sort based on the second digit. And the rule is if you have two things with the same second digit, you've got to preserve their current order. Okay, so 2 is going to be the smallest, so this is going to be 6222. And then 4, so this one will come first. 5541, and then 2147, and then 2446, 5560, and 4276, and 3185. And then you sort based on the third column. So the ones come first, 2147, 3185. And then the 2s, 6222, 4276, and then the 4, 5541, and then 5560. And then you sort on the most significant column, 2147, 3185, 4276, 5541, 5560, 6222, and you're done. Yeah?
So in this case, there are 4 numbers each, right? But
Mm-hmm.
if there's 5 numbers.
So add some zeros on the left so that all these things have the same width. Or just pretend there's a 0 there.
So this reduces the amount of passes to how many digits you have per number.
Mm-hmm.
But there's still a lot of passes even with 4 numbers.
So the number of passes is the number of digits or characters. And if we assume we're sorting 12-digit numbers, right, it's 12 passes, it's a fixed number. So that's 1 trillion numbers. So it would take 12 passes, and each pass we have to go through basically order n to find, let's see. So each pass takes basically 10 steps if we have 10 digits, right? Go through and find all the zeros and copy those into your output array. Go through and find all the ones, copy those into your output array, right? So your inner pass is roughly 10 times n, and your outer pass in this case was 4 digits. So that's order n. Yeah. So that's kind of an interesting sort. Yeah.
So how's this swapping happening?
We're copying from an input array to an output array. So keep an index on the output array, and like I say, first pass, look for all the things that have a 0 in the position we're looking at. And as you encounter one, copy it to the output array and keep going.
So are you just creating new output arrays, or are you
Yeah.
copying back to the original?
You can copy back to the original if you want. That's another constant factor of n. Or you can just have a bunch of output arrays. So you can do this for numbers, you can do it for words, you can do it for anything that you can break down into these character positions, right? As long as you can work sort of one position at a time. It's a little counterintuitive because usually we would think of sorting by the leftmost digit first, because that's the most significant one. But you got to start with the least significant digit, or more precisely, you have to end with the most significant one. There's also the fact that you need to preserve order. When you have two things that have a 4, they've got to stay in the same order. And some sorts will randomly, not randomly, but effectively randomly change things around if they're equal when you try to sort them. So you need to preserve the order of things that are equivalent. But it's an intriguing sort. It's a different kind of feel. I like it, but I don't code up sorts as a matter of practice. But there's cases where you might be trying to sort things that have this sort of column by column characteristic, and a radix sort might work well.
Is there a best case to use?
A best? Well, so that's another interesting question is what if we did this on binary? Couldn't we do a radix sort on that? And it's a really easy radix sort because we only have 2 symbols, 0 and a 1. So we'd start on the,
You would normally start on the right.
yeah, so we'd start on the least significant bit, find all the things that end with a 0 and put that into our output array in order, and then find all the things that end with a 1, which is basically everything else, and put that into the rest of our output array. And then go through that array and look at the second bit and copy the 0s first, and then copy the 1s, and go on like that. So it's 2 passes times n times the number of bits, and there's a sort.
You could do that from the left too, right? It would just be different.
Starting from the left?
Yeah, because if you start with the most significant bit, it's going to kind of act like a bubble sort where everything just sinks to the bottom or rises to the top.
The problem is when you get to your last pass and you're over here, this very insignificant bit can totally change the order, right? Basically, all your even numbers are going to come out before all of your odd numbers, which might be useful in some way.
You mean in binary?
Yeah, yeah.
But I guess I can see that within it.
Yeah. So if you did this in a general radix, you might be able to find all your composite numbers first before all your primes or something. So that's a radix sort. It's just another approach. So that's arguably order n, although there's some big constants in there. But for really, really large sets of data and a high radix, it can be pretty efficient. All right, other questions? We've got 8 minutes to start another sort. Let's look at Quicksort.
There's a cool video I want to show you about all the sorts.
Yeah?
Much better than the one in
Oh, okay. Can you put a link on Canvas?
Sure.
Cool. Okay, I'll check it out. Yeah, we didn't get to do giraffe sort.
Links you to your own video.
What?
Links you to your video.
Yeah, right. All right, let's look at Quicksort. And I think this is the sort that a grad student came to his advisor or he was on the job, right? And he was asked to code up a sort, and his boss told him what kind of sort to use, and he said, actually, I've got a faster sort than that. And his boss is like, no, you don't. And so he bet him like a bottle of whiskey or something that his sort wasn't more efficient, and he went off and he proved it, and he got the bottle of whiskey, which they split. Some story like that, but I think that goes with Quicksort. This is a weird sort, okay? It's got multiple steps to it. It's another divide and conquer. Merge sort is a divide and conquer, right? Cut the problem in half, solve the sub-problems, put the solutions together. That's classic divide and conquer. So is Quicksort, okay? But the algorithm is different, and this is the sort that works best on unsorted initial data. So sometimes you actually randomize your data before putting it in a Quicksort, just to make sure nothing funny is going on. So let me take you through a first pass or two on a Quicksort, and we'll talk about the details of this more carefully next week. So here's an array of data we want to sort. So there's a notion of a pivot. And a pivot, we usually just pick the rightmost number to be our pivot point. And here's the idea. Our goal is to move the pivot to the proper place in the array. Ultimately, once the array is sorted, where is the 3 going to end up in the array? That's what our first pass of a Quicksort basically decides. So it will go through a variety of steps, and in some way it will decide, well, I picked a really bad pivot, but it will decide that, so let me change this on you. Nah, I'll leave it. It'll decide that the 3 should go right here, right? Because the final sort order is going to be 2, 3, 4, 5, 6, 7, 8, 12, 16. Okay, once we have the pivot in the correct spot, we never have to worry about this number again. It doesn't have to get involved in any sort operations. Okay, once the pivot's in the correct spot, we now have 2 subarrays. And in addition to having the pivot in the correct spot, everything smaller is to the left, and everything larger is to the right. So after this first pass, we may end up with something like this. 2, 3, 4, 6, 5, 8, 7, 12, 16. I might have lost a number. That's okay. So we'll end up with a 3 in the correct spot. Everything to the left is smaller. Everything to the right is larger. Which means now all we have to do to sort the entire array is sort this subarray and sort this subarray. We don't have to interleave them or anything like that, because this is right where it belongs in the final output array. So if we sort everything to the left and we sort everything to the right, we're finished. And the way that we sort these subarrays is by using a Quicksort. Okay, so that's going to be the basic approach. We're going to start off with an array of data. Yes?
So, in the initial array that you had there, you have 4, then 2, then 6, 5. But after the first pass, you've already got the 2 and 4.
Yes.
before you do another Quicksort.
Yeah. So each pass will put the pivot in the correct spot and cause things to be such that everything smaller than the pivot is to the left, everything bigger is to the right. Which then means all you have to do is sort what's on the left and the right, and you're done. And we do that by calling Quicksort. So it's another divide and conquer, and it'll tend to be order n log n, although in pathological cases it'll be n squared.
How did he get his file?
He proved that this was more efficient than whatever the method was that he'd been asked to implement. I don't remember what it was, but he showed that this was more efficient. There's still new sorts being developed, even in the year 2000 plus. Every now and then someone comes up with an embellishment. All right, so this will be a divide and conquer. So Monday we will talk about how this whole pass works. And it's a process of starting from both ends and moving in and swapping things periodically. And when you're done with that pass, we've got this set up, and then the rest is just recursion. All right, so we'll play with that on Monday. Come in tomorrow if you want to work on things. I may be setting up a Linux laptop tomorrow, so if you want to play around with Linux on a machine, bring it in and we can set up Linux on it.